The topic today is the scattering matrix. The name itself should make it obvious to you that this is a central topic in the quantum theory of scattering. But before we get into that, let me quickly recall for you what we had talked about in the last couple of lectures. Let me remind you before that we are working in the Heisenberg picture so that manifest Lorentz covariance is easier to demonstrate. But that means that our states do not evolve in time, but operators, of course, do. And in this context, we defined two distinct classes of states. First, the in states, denoted by psi plus with a label alpha. Alpha here is a bunch of single particle labels, P1, sigma 1, N1, P2, sigma 2, N2, and so on, where Pi is the force momentum of the ith particle, sigma I is the spin z component for the ith particle, Ni is a species label for that particle. And when we say that the system is in an in-state psi alpha plus, what we mean is that this will be found to have particle content alpha, independent free particles with labels given by those in alpha, if the measurement is done at very, very remote times in the past, that is, in the limit t goes to minus infinity. Let me remind you once again, the state psi alpha plus, once is created, is constant throughout, it does not evolve in time. However, the results we obtain from measurements do not depend only on the state, it also depends on the operators which actually change with time. And it is these results which, when carried out in the remote past, would reveal that our system has free particles effectively with these labels. A counterpart to the in states are the out states, and they are denoted with a minus in our notation. Psi beta minus will be found to have particle content beta, that is P1 prime, sigma 1 prime, N1 prime, P2 prime, sigma 2 prime, N2 prime, and so on, if the measurement is carried out in the remote future, that is in the limit t goes to plus infinity. And in the last lecture we saw that we could, at least formally, write both psi alpha plus and psi alpha minus, the in and out states of the particle label alpha, in terms of the free particle state phi alpha. Here, we are talking about a situation where the Hamiltonian capital H can be broken down into two parts, H0, which is the free particle part, and under which these free particles just do not interact with each other, but just evolve in time with simple trivial phase factors, and an additional interaction piece, the potential or the perturbation capital V. In such a situation, we have shown that you can write down psi alpha plus or minus as the result of an operator omega at minus plus infinity acting on the free particle state phi alpha. And here omega is a tau dependent operator. Omega of tau is e to the ih tau times e to the minus ih0 tau. And when you take the limiting value of this operator at time tau going to minus infinity and apply that on phi alpha, the free particle state, you get psi alpha plus. If you do the same thing for the limiting value at plus infinity, you end up with psi alpha minus. These operators are called Moeller operators, and as we will see today, they are very useful in the theory of scattering. On the right hand side, you see another expression for psi alpha plus minus, which is not really a solution for psi alpha plus minus in terms of phi alpha, because what you can see here is psi alpha plus minus is given by the free particle set phi alpha plus a correction term, which is E alpha minus H0 plus minus I epsilon inverse acting on V psi alpha plus minus. This is called the Lippmann-Schwinger equation. It is not a solution for psi alpha plus minus because the unknown, the in and out states, are actually stuck on both sides of the equation. But this, among other things, gives us a nice possibility for perturbatively figuring out how psi alpha plus minus differs from phi alpha step by step, by which I mean in powers of the interaction V. As we will see during the course of today's lecture, both the Moeller operator approach and the Lippmann-Schwinger approach, despite being rather formal, are very, very useful in figuring out things about the scattering matrix, which is going to be the central thing in our discussion today. Now, why are the in and out states so important in scattering theory? Let me remind you that in a typical scattering experiments, particles come in from very far away, interact among each other, and the same particles or maybe some new particles created because of the interactions go out from each other, away again, and in the remote future, these particles again are too far away from each other to be interacting. So particles start out non-interacting because they are too far away, come close, interact, and then they go away. So that is how a typical scattering experiment is done. When the incoming state is prepared, you prepare that with a particular particle content alpha. Remember, when I say particle content, I don't mean just the identities of the particles which are coming in, but also their force momentum levels, the spin component labels, and so on. So you have created a system where two or more particles with definite force momentum, definite spin are coming in, interacting with each other. If you were to observe the system, in the remote past, it would reveal the presence of these non-interacting free particles. So the state in the remote past, and remember, because we are using the Heisenberg picture, the state all along is psi alpha plus. On the other hand, when we detect particles, we do that long time after the scattering event takes place. And again, now the particles are free from each other. And you might very well detect them with a different particle content, let's say beta. And you would expect the particle content to change. Not just the identity of particles, that's a possibility, but even with the same particles, you could have at least changes in momentum or spin component and so on. So when you are trying to detect the final state, what you are trying to detect is whether the state of the system can be described by the particle content beta in the remote future. This, of course, means that what you're talking about is the state psi beta minus. In other words, you have created the system in psi alpha plus and you're trying to find out the probability of observing the system in the state psi beta minus. Now, as you all know, the quantity that you need to calculate here is the probability amplitude for this happening. If a system is in state psi alpha plus, and you want to detect it in state psi beta minus, the probability amplitude that you have for this is the inner product of the state psi beta minus with the state psi alpha plus, and it is this inner product that gives us the beta alpha element of the so-called scattering matrix. Since typically the particle labels beta and alpha can take infinitely many values, we are talking about a potentially infinite dimensional matrix here, whose components are given by this inner product. And this is the so-called scattering matrix, or S matrix for short. At the risk of belaboring this point a bit too much, let me stress once again that when we created the system with particle content alpha in the remote past, it was in the state psi alpha plus. But not only that, it is always in the state psi alpha plus, which is why we are not saying that the system was in psi alpha plus and has evolved to something else, and then we are trying to figure out its particle content. We are saying that the system is in psi alpha plus, and we are trying to detect whether it is in psi beta minus. Of course, the probability proper is the modulus square of this quantity, S beta alpha. Now, the difference between the in and the out states is, of course, basically because of the interaction. If H had been the same as H0, the Moeller operator omega would have trivially been the identity for all tau values, and therefore psi beta plus minus would both have been equal to phi beta. So if there are no interactions, then psi beta minus is exactly the same as psi beta plus. So then the matrix element S beta alpha would be the inner product of two in states with possibly different particle contents. And we had already seen in the last lecture that the in states as well as the out states are orthonormal complete sets, and therefore in such a case S beta alpha would simply be psi beta plus inner product with psi alpha plus, which is delta of beta minus alpha. That's the orthonormality coming into play. Which is why when you talk of the rate of the interaction which takes place, you take away the delta beta minus alpha from the S beta alpha, because delta beta minus alpha would have been there even in the absence of an interaction. And we talk about this quantity modulus of S beta alpha minus delta beta minus alpha whole square. Now since S beta alpha transforms the in states essentially into out states, taking a complete set of orthonormal states into another complete set of orthonormal states, it is a standard result in linear algebra that this matrix here is a unitary matrix. Let us now take a look at a slightly more detailed proof of this, starting from the very definition of unitarity of a matrix. A matrix S is called unitary, of course, if S dagger is the same as S inverse. In other words, if S dagger S is the identity, and equivalently, if S dagger is the identity. I did say equivalently right now, but there is a catch there. For finite dimensional matrices, S dagger S being the identity immediately implies that SS dagger would also be the identity. So these two statements would end up being equivalent. However, for infinite dimensional matrices, this equivalence is not necessarily true. So we really should show that both S dagger S and SS dagger are infinite dimensional matrices whose components are the components of the identity, or simply delta of beta minus alpha for the beta alpha component. So let us take a look at S dagger S first. The gamma alpha component of S dagger S is simply the gamma beta component of S dagger multiplied by the beta alpha component of S summed up over all possible beta values. And here, since beta can potentially be a continuous variable as well, this summation is indicated formally by this integral over d beta. Let me remind you that when you use this kind of notation, it means you are going to integrate over all the continuous labels like the momenta and also sum up over the discrete labels like the spin components. Of course, the gamma beta element of S dagger is nothing but S beta gamma's conjugate, and that is what we have used here. Now let us go by the definition of S beta alpha. S beta alpha, let me remind you, is just the inner product psi beta minus with psi alpha plus. And S beta gamma, whose conjugate is sitting here, is the inner product between psi beta minus and psi gamma plus. Of course, the order matters because if we were to flip the order of these two, as we have done here, the number becomes its complex conjugate, which is exactly what we want. So this really is the integral over beta, or sum over these labels beta, of the product of these two inner products, psi gamma plus psi beta minus and psi beta minus psi alpha plus. But you would realize that this combination, when summed up over all possible beta values, actually is a resolution of the identity. And what that means is that this entire integral is really nothing but the inner product between this state psi gamma plus and this state psi alpha plus. The inner product of the two in states here, and since in states are orthonormal, you end up with delta gamma minus alpha for the value, which is exactly the gamma alpha element of the identity matrix in this notation. Let me remind you once again that in this proof what we have used is that the out states, the states labeled by minus, form a complete set, complete orthonormal set, and the in states are orthonormal. Using both of these together, we have managed to show that S dagger S is the identity. What remains to be shown is SS dagger is also the identity. To show that SS dagger is the identity, we proceed in exactly similar fashion. We take the gamma beta element of S, multiply that by the beta alpha element of S dagger, that's S alpha beta's conjugate, sum up over all possible values of beta. And again, using the definition of the S matrix, we get this to be the inner product between psi gamma minus and psi beta plus. That of course is S gamma beta. And here we have already taken the conjugate of S alpha beta. S alpha beta, remember, was psi alpha minus's inner product with psi beta plus. Because of the conjugation, it has become the inner product of psi beta plus with psi alpha minus. And in this case, what we use is the completeness of the in states. That is, when you sum up over all beta, this particular combination is the identity, to show that this is psi gamma minus inner product with psi alpha minus. And then use the orthonormality of the out states to show that this has to be delta of gamma minus alpha. In other words, S dagger has to be the identity. So we have managed to prove that both S dagger S and SS dagger is the identity matrix here. And that completes the proof that the S matrix is a unitary matrix. Now, during the course of these lectures, we will see exactly how useful the S matrix is. And given the amount of utility it has, it follows that there are several different approaches to this and different ways of talking about it. And each of them are useful in their own way. We are now going to talk about another avatar of the S matrix, something which is related to the S matrix directly, and this one is called the scattering operator or the S operator. So we are defining this operator here to be one whose matrix elements, the beta alpha matrix elements, is going to be S beta alpha. But here, let me be very clear, here when we say matrix element, we mean in the basis provided by the free particles, that is the H0 eigenstates, not the in or the out states which are H eigenstates. So the definition here is the S operator is defined along these lines. When S acts on a free particle state with particle labels alpha, that is phi alpha, it produces a vector. When you take the inner product of this vector with phi beta, which is again a free particle state, a H0 eigenstate with particle content beta, the complex number that you get is equal to S beta alpha. Note that this is the definition of the S operator. S beta alpha has already been defined to be psi beta minus's inner product with psi alpha plus. Using that and the relationship between the in and out states with the free particle states, we can make several interesting observations about the S operator. And that's what we are going to do next. Let me remind you that the in and out states with a given particle content, psi plus minus alpha, can be obtained by applying omega minus infinity or omega plus infinity, respectively, on the free particle state phi alpha, same particle content, but this time evolving freely. And as we have already seen before, omega here is a tau dependent operator given by e to the IH tau multiplied by e to the minus IH0 tau. It is the limiting values of this omega tau operator in the limits tau going to minus infinity and tau going to plus infinity, which act on the free particle state to give us the in and out states with the same particle content. Of course, psi beta minus is then omega plus infinity acting on phi beta, psi alpha plus is omega minus infinity acting on phi alpha. The reason why I have written these two things separately is that the inner product between these two vectors is exactly what S beta alpha is. So, by the definition of our S operator, inner product between phi beta and S phi alpha, which is S beta alpha, which again by its definition is psi beta minus inner product with psi alpha plus, this actually is the inner product of omega plus infinity acting on phi beta, that's psi beta minus, and omega minus infinity acting on phi alpha, which is psi alpha plus. We now use the definition of the adjoint of an operator to move the omega plus infinity from here onto the other vector. Of course, in the process, it changes to its adjoint, omega dagger infinity, and then it's multiplied by the original vector sitting there, omega minus infinity phi alpha. So note that phi beta's inner product with S phi alpha is the same as phi beta's inner product with omega dagger plus infinity, omega minus infinity acting on phi alpha. And since beta and alpha can be arbitrary free particle states, this actually implies that S has to be omega dagger plus infinity times omega minus infinity. We often write this as U with two arguments plus infinity and minus infinity, where U at tau comma tau 0 is defined to be omega dagger tau, omega tau 0. Of course, when you take the limit of tau going to plus infinity and tau 0 going to minus infinity, you are going to get the operator that stands in for S. And using the definition of omega tau, what we get here is the adjoint of omega tau dagger, which is e to the plus IH0 tau e to the minus IH tau. And here, omega tau 0 gives you e to the IH tau 0 into e to the minus IH0 tau 0. And when you take them together, you get e to the IH0 tau. These two things join together to give you e to the minus IH tau minus tau 0. And you follow it up with e to the minus IH0 tau 0. The notation U of tau comma tau 0 looks very much like a time evolution operator, which actually evolves a state from the time tau 0 to the time tau. But once again, let me remind you that in the Heisenberg picture, states do not evolve, and the actual evolution operator in the Heisenberg picture is actually identity. States don't change with time. Actually, this does happen to be the time evolution operator in the interaction picture, something we are going to talk about later. But for the time being, this is just an operator which, in the limit plus infinity for tau and minus infinity for tau 0, gives us our scattering operator S. Now the Moeller operators provide us with one way of connecting the in and the out states with the free particle states. The other approach, as I have already mentioned, is via the Lippmann-Schwinger equations. I say equations basically because there are two, one for the in states, the other for the out states. Of course, you write them together, and as I have already said, psi alpha plus minus is phi alpha plus this operator E alpha minus H0 plus minus I epsilon's inverse acting on V psi alpha plus minus. Exactly why do we use the plus minus I epsilon, with the prescription of course that epsilon is going to be taken to be 0 in the limit, has been explained in quite some detail in the last lecture. Let me remind you that the other thing that we did there was to expand out this V psi alpha plus minus, which is a vector in the Hilbert space, in terms of the complete orthonormal set of free particle states, phi betas. And when you do that, this V psi alpha plus minus gets replaced by integral over d beta, phi beta times this particular inner product, phi beta inner product with V psi alpha plus minus. And using the fact that phi betas are H0 eigenstates with eigenvalue E beta, you can bring this operator inside and then convert this into an equation which involves numbers mostly. So basically psi alpha plus minus can also be written down in this particular form, phi alpha, which is of course the same as this one, plus integral over d beta, t beta alpha plus minus times phi beta. This t plus minus beta alpha is nothing but just this particular inner product, which of course is a complex number, divided by what you get when E alpha minus H0 plus minus I epsilon inverse acts on phi beta, namely E alpha minus E beta plus minus I epsilon. This is another form for the Lippmann-Schwinger equation. Now, let me also remind you that in order to be able to distinguish the in and out states from the free particle states physically, we had to consider not the states directly themselves, because they are Hamiltonian eigenstates for their respective Hamiltonians, H for the in and out and H0 for the phi. And as time evolves, they would actually just pick up physically meaningless phase factors. So saying that one particular time evolved vector is the same as another particular time evolved vector actually makes little sense. In order to make sense of this, what you need to do is work with superpositions for the free particle states and the corresponding superpositions with the same weighting function g alpha for the in and out states. And the Lippmann-Schwinger equation for these superpositions essentially becomes psi g plus minus t. This of course is not the wave function or not the state vector at the time t. It is actually a time displaced version of the state vector viewed from another observer whose clock is displaced by minus t compared to the original observer. Anyway, we have already discussed all this in some detail in the last lecture, so no point in repeating that over and over again. Psi g plus minus t is given by phi g t plus this double integral over alpha and beta of e to the minus I e alpha t times t beta alpha plus minus multiplied by phi beta divided by e alpha minus e beta plus minus I epsilon. Now in the last lecture, we had used this form and contour integration to justify why we are using plus or minus I epsilon for the in state and the out states respectively. We are going to actually proceed along similar lines now, but with a very different aim. We have already established that using plus I epsilon in the denominator makes this rather nasty looking double integral vanish in the limit t goes to minus infinity, which is why the combination psi g plus t goes over to phi g t in the limit t goes to minus infinity, thus justifying that these are actually in states. Similarly, using minus I epsilon in the denominator would actually make this double integral vanish in the limit t goes to plus infinity, justifying why the psi g minus are actually out states. Let me remind you that in order to do this, what we had done was rather cavalierly, at least from a mathematical point of view, interchange the beta and the alpha integrals and worked out this alpha integral first. And this of course depends only on beta, and we call this scri beta, script I beta plus minus. So this integral piece actually becomes integral over beta scri beta plus minus times phi beta. And then what we had done was to show that in this integration over alpha that we had carried out to figure out scri beta plus minus, we are actually integrating over all momentum labels for the individual particles, which of course means that we are also integrating over the zeroth component of the momentum labels, which are the energies of the individual particle. And then what we did was realize that we could change the variables in such a way that one of the integration variables became the total energy E alpha of these particle states labeled by alpha, and then use contour integration techniques for the integral over E alpha. This showed us that in the limit t going to minus infinity, scri beta plus would vanish, making this term go away, and so in that limit, psi g plus t would be exactly equal to phi g t. A similar thing had been done for the limit t going to plus infinity, which would show that scri beta minus would vanish in that limit, leading to psi g minus t, giving us phi g t. Now, what we are going to do now is we are going to do something very similar, except that we are going to look at psi g plus t, the combination of the in states, but in the limit t goes to plus infinity. So this is what we are looking at. There should be an extra phi beta here, of course. And we are going to focus on what scri beta plus becomes in the limit t goes to plus infinity. And that's going to help us figure out how the superposition of in states would look to an observer for whom that time is actually plus infinity. So, just to remind you, this is exactly what we did in the limit t goes to minus infinity. This integral over E alpha was carried out over the real line, over the entire real line of course, despite the fact that the integration only takes place from E alpha going from 0 to infinity. We could actually use exploit the fact that G alpha vanishes beyond a particular range to convert this to an integral over the full line, and then use the standard trick in contour integration to close the contour. Now this is where things differ in the two limits. In the limit t goes to minus infinity, we had to close the contour with a semicircle, or at least a curve which is topologically a semicircle, in the upper half plane, because the contribution from this contour would die out in the limit t goes to minus infinity. Here, on the other hand, we are looking at the limit t goes to plus infinity, so the closure has to come in the lower half plane. For the case t going to minus infinity, the contributions which could have come from the poles of G alpha or t plus beta alpha in the upper half plane would all vanish because of the positive imaginary parts present for E in these poles, which would make the factor e to the minus I E alpha t go off to 0 exponentially. The one pole which was very close to the real line and would not have suffered from this exponential suppression happened to be at E beta minus I epsilon, so was outside the contour, which is what made this contour integral and hence this integral over E alpha vanish. But this time, now that we are using the semicircle in the lower half plane to close the contour, this particular pole, which I have shown away from the real axis but actually is infinitesimally close to the real axis in reality, is the one which is inside the contour, and this is the one pole which is going to contribute. All other poles, the poles which come from G alpha or T plus beta alpha, which are in the lower half plane and hence are inside the contour now, would not contribute for the same reason that the semicircle doesn't contribute in the limit t goes to plus infinity. All of these would have a E alpha with a negative imaginary part, and now e to the minus I E alpha t would have an exponentially damped factor which will vanish as t goes to plus infinity. So the only non-zero contribution comes from the pole at E alpha equals E beta minus I epsilon in the limit where epsilon goes to 0. Now what you can do is simply use residue theorem to evaluate the E alpha integral, and that will tell you that you get a 2 pi I from the E alpha integral from this particular pole, which essentially means that you have to replace every E alpha here by E beta minus I epsilon. This particular part will go away. That's basically how you calculate the residue for a simple pole. You multiply by this denominator and replace everything else here, every E alpha here, by E beta minus I epsilon. And this is what the final result becomes. Remember, we have not completed the integration over alpha. Alpha actually has many labels, all particle momenta, particle energies and so on. It's just the result of the E alpha integration that has essentially given us a delta E alpha minus E beta, which forces all the E alphas to become E beta. In particular, the e to the minus I E alpha t becomes e to the minus I E beta t and can be taken outside the integral. G alpha may be a more complicated function of the alpha parameters and would usually involve other parameters than the energy. So we are leaving it as G alpha with this delta E alpha minus E beta still stuck, reminding you that the energy E alpha has to be replaced by E beta throughout. So this is what chi beta plus is in the limit t goes to plus infinity. This shows us that at least in the limit of very large positive values for t, this is what psi g plus t becomes. This first thing here is nothing but phi g of t, and this is exactly what you get when you substitute this for chi beta plus in the rest of the expression. But now we know that psi g plus t would essentially behave like psi alpha plus a superposition with the weight G alpha multiplied by e to the minus I E alpha t. And that, if you use the fact that the out states, psi beta minuses, form a complete orthonormal state and expand the psi alpha plus in terms of that, ends up giving you this expression. The integral of d alpha e to the minus I E alpha t, G alpha, these are all alpha dependent, independent of beta, so they have been moved out here. But now you have this integral of over beta, psi beta minus times this matrix element, which is nothing but S beta alpha. Now, because S beta alpha has an energy conserving delta function, you can use that to just say that the energy e to the minus I E alpha t that you have here is actually the same as e to the minus I E beta t, and then interchange alpha and beta integrals to write this as d beta psi beta minus e to the minus I E beta t times this particular integral d alpha g alpha S beta alpha. Now, remember we have already shown using contour integration that this is what psi g plus is. And we have also seen from the definition that this is what it should be. Using the fact that in the limit t goes to plus infinity, a superposition of psi beta minus states, out states, essentially looks like the corresponding superposition for the free particle states, and using this integral here as g tilde beta, the new weighting function, what you end up with is psi g plus t in this limit t goes to plus infinity must match this. The same superposition with phi beta, the free particle states. But now realize that we have already written psi g plus t using the contour integration technique as this, a superposition of different phi beta values with a phase factor e to the minus I E beta t times this particular factor. And so, what you must be able to say is that this integral here is the same as g beta minus twice I pi delta E alpha minus E beta G alpha T beta alpha plus whatever you had inside this bracket. So finally, putting all of these together, you realize that S beta alpha must have a delta beta minus alpha piece, which will give you G beta when you integrate G alpha multiplied by that, and the rest will be minus twice I pi delta E alpha minus E beta T beta alpha plus. So what we have done is we have been able to reduce the matrix element S beta alpha in terms of the Lippmann-Schwinger elements T beta alpha plus. Apart from this factor of twice I pi and this energy conserving delta function, T beta alpha plus essentially is the interaction part of the S matrix. Delta beta minus alpha, of course, is what would have been there without an interaction. This is the additional piece which the interaction brings in. This particular result for the S matrix element written in terms of the Lippmann-Schwinger matrix element is of great importance for practical reasons, because you can perturbatively expand T beta alpha and get a result which gets better and better, hopefully, as you go further and further higher in the order of perturbation. But it is also useful for several formal purposes. In what comes next, we are going to explore few of those applications. But let me point out that T beta alpha plus, which is of course phi beta inner product with V psi alpha plus, has a very simple approximation which we have talked about earlier as well. If the potential is weak, we may use the approximation that psi alpha plus is the same as phi alpha in this expression, and then this immediately gives us a formula for S beta alpha, at least to first order in the potential. Apart from the delta beta minus alpha, you get minus twice I pi delta E alpha minus E beta times the inner product of phi beta with V phi alpha, or as is often called, the beta alpha matrix element in the free particle basis of the potential V. This particular approximate value for the S beta alpha is approximate, of course, because you have replaced psi alpha plus with phi alpha, which is an approximation. And you can improve upon this, but this particular approximation is called the first born approximation. And very often in scattering theory, using this is enough to get useful results about physical systems. In the rest of the lecture, I am going to give you alternative derivations for two of the very important results that we have already derived before. One of them involves the orthonormality of the in and the out states, something we had proven in the previous lecture. And the other important result that I am going to rederive for you now is the unitarity of the S matrix, something which we worked out near the very beginning of this particular lecture. What we are going to discuss is an alternative derivation, one using the Lippmann-Schwinger equations. While the results have already been derived once, it is always a good thing to have multiple ways of looking at a particular thing, which helps you to understand things a lot better. Moreover, the techniques that we are going to use here are also quite useful in various different branches and will be used later on as well. Apart from this, a purely practical advantage of these alternative derivations is that they do not require you to take limits of some parameter t going to minus infinity or plus infinity. Such limits are always tricky, and we have often interchanged the order of taking these limits with taking inner products and so on, and that is always something which is slightly complicated to justify with complete mathematical rigor. Those steps could be made rigorous, however that would take way too much of our time. So we have taken the phases way approach where we assume that these kind of things can always be done. As I said, the advantage of the kind of derivations that I am going to talk about now is that such limits do not have to be taken. And of course, we are going to use the Lippmann-Schwinger equation to do that. As you all must recall, the Lippmann-Schwinger equation simply relates the in and the out states for a given particle label set alpha with the corresponding free particle set by this following equation. Psi alpha plus minus is phi alpha plus a correction because of the perturbation given by E alpha minus H0 plus minus I epsilon's inverse acting on V times psi alpha plus minus. Now, in order to carry out both of our alternative derivations, what we are going to do is take a look at this particular quantity. The inner product of psi beta plus minus with V psi alpha plus minus. Or basically, the matrix elements of the perturbation V in the basis of either the in states or the out states. But what we are going to do here is the following. We are going to evaluate this particular inner product in two different ways. One in which we replace this psi alpha plus minus by the expression which Lippmann-Schwinger equation gives us. In the other, we are going to replace this psi beta plus minus by the corresponding Lippmann-Schwinger version. Now these two results must of course agree with each other, and that's going to give us identity between the matrix elements t plus minus beta alpha. So let us see how that is done. First, let's try to evaluate this quantity by replacing psi alpha plus minus on the right here by this expression. So we get the inner product of psi beta plus minus with V phi alpha, that's of course V acting on this, plus V E alpha minus H0 plus minus I epsilon inverse, V psi alpha plus minus. So this of course splits into two inner products, psi beta plus minus V phi alpha, and the other one, well, we have just massaged this a bit by bringing this V from the right hand factor to the first factor. And that, of course, uses the fact that V is a Hermitian operator, so V dagger, which is the operator which should really be sitting here, is the same as V. Now let us take these two things in step. Recall that psi beta plus minus V phi alpha is actually related to our T plus minus alpha betas. Well, this is actually the complex conjugate of the inner product of the two vectors taken in the reverse order, V phi alpha inner product with psi beta plus minus, and Now what you can do is move the V from here to here using again the hermeticity of V, and this thing here is nothing but our matrix element T plus minus alpha beta. So T plus minus alpha beta's conjugate is exactly what is sitting here. What about the second term? In the second term, what we do is we realize that V psi alpha plus minus sitting here can be expanded in terms of the free particle states like this. And in fact, we have already seen this when we looked at the second version of the Lippmann-Schwinger equation. And using the fact that phi gamma V psi alpha plus minus is exactly what T gamma alpha plus minus is defined as, we see that V psi alpha plus minus essentially has this expansion in terms of the free particle states. And we now use that. Of course, when you replace V psi alpha plus minus here by this expression, you can use the fact that H0 has phi gamma as an eigenstate with energy E gamma, and that simplifies the expression substantially. So what you get for this particular matrix element is, on the left, we are replacing V psi alpha plus minus like this. On the right, we have the same replacement, but of course the dummy variable has been changed here, and we have E alpha minus H0 plus minus I epsilon inverse sitting here. This of course becomes a double integral over both gamma and gamma prime, with T plus minus gamma beta's conjugate coming out. Remember, the inner product is antilinear in the first factor. And let me warn you, this is the opposite convention to the one which the mathematicians use. This is the one which physicists use about the inner product in a complex vector space. And it's again linear in the second factor. So T plus minus gamma prime alpha comes out, and because of the fact that phi gamma prime is an energy eigenstate for H0, you get E alpha minus E gamma prime plus minus I epsilon inverse sitting here, which can also of course come out of the inner product. So we are left basically with the inner product between phi gamma and phi gamma prime, which, as we know, the free particle states being orthonormal, is simply delta gamma minus gamma prime. And this helps us to trivially evaluate the gamma prime integral. Remember, delta gamma minus gamma prime essentially means it's a Dirac delta function for all of the continuous labels in gamma and gamma prime, and Kronecker deltas for all the discrete labels. And of course, this integration here is integration over the continuous variables, summation over the discrete ones. But the net effect is that this integral over gamma prime can be done trivially, and all the gamma primes get replaced by gamma. So this is the expression that you end up with for the second term for our expression. So psi beta plus minus comma V psi alpha plus minus turns out to be the conjugate of T plus minus alpha beta plus this integral d gamma T plus minus gamma beta star T plus minus gamma alpha times the inverse of E alpha minus E gamma plus minus I epsilon. So that, as I told you, is one way of evaluating this particular matrix element. We can of course evaluate it in the other way, and that's exactly what we are going to do now. In the alternative evaluation, what you do is replace the psi beta plus minus in the first factor of the inner product by whatever the Lippmann-Schwinger equation gives us. So of course, it's the same thing except that all the alphas have changed into betas. And you just have V psi alpha plus minus here. Now, once again this splits into two pieces, and what we are going to do here next is this one we can easily identify. This is actually T plus minus beta alpha. On the other hand, in order to calculate this one, what we will do is we are going to first move this to the right using the fact that this is almost Hermitian. Actually, we are using its adjoint here. So the plus minus I epsilon moves to this side because minus plus I epsilon. The rest stays the same. And now you have V psi beta plus minus and V psi alpha plus minus on both sides, which we will replace in terms of their expansion from free particles. And by carrying out an exactly similar calculation as the one I had already done a few minutes earlier, and I'm not going to bore you with a repeat of that, you can easily check that this is going to be T equal to T plus minus beta alpha plus integral over gamma T plus minus gamma beta star T plus minus gamma alpha E beta minus E gamma minus plus I epsilon inverse. So note that these two expressions here, we should of course be the same thing because they are the same quantity, namely this quantity evaluated in two different ways. Well, the expressions here are very similar, but in one you have T plus minus alpha beta's conjugate, in the other you have T plus minus beta alpha, and the integral that comes in here, they are also very similar, but in one you have E alpha minus E gamma plus minus I epsilon inverse, in the second you have E beta minus E gamma minus plus I epsilon inverse. Equating the two immediately gives us this result, that basically what I have done is subtracted this from this and equated the result to 0 and changed sides a bit to get T plus minus alpha beta star minus T beta alpha plus minus is nothing but what you get if you take this integral and from that subtract this integral. We can then simply calculate this by simple algebra, and this is what you end up with. Notice that the numerator here, E alpha minus E beta plus minus twice I epsilon, does not depend on gamma, so it can be taken out of this integral. So, our first calculation will start from this by simply dividing both sides by E alpha minus E beta plus minus twice I epsilon. Actually, it's a negative of that, so that this minus becomes plus here. And here, I've just taken the whole thing inside the conjugate sign. Note that what you are doing is you are dividing by E alpha minus E beta plus minus twice I epsilon's negative, which is, of course, E beta minus E alpha minus plus twice I epsilon. That's what you are really dividing by. So, since I've taken this inside the conjugate, it's now E beta minus E alpha plus minus twice I epsilon. And the conjugate of that whole thing has been taken. On this side, you simply have, well, the integral over gamma of the product of two factors which look very similar. You have T plus minus gamma alpha by E alpha minus E gamma plus minus I epsilon. And the other factor is T plus minus gamma beta by E beta minus E gamma plus minus I epsilon. But the conjugate of that. Note that this is the factor that you had, and this is what you end up with because of the conjugation. Now, the next step is straightforward. Notice that the I epsilons are there only to tell you that the poles will not be on the real line, but they will be moved very, very slightly away from the real line. So the precise magnitude of epsilon doesn't really matter because you're going to take the limit as epsilon goes to 0 anyway. Which is why you can actually replace the twice I epsilons here simply by I epsilon, because all that this is telling you is that in the limit epsilon goes to 0, what these two sides are going to be equal. And of course, I've moved this thing to the other side. Now, in order to use this, we are going to consider this quantity, f plus minus beta alpha, which is given by delta of beta minus alpha, plus basically this factor. Importance of this is that according to the Lippmann-Schwinger equation, you can easily see the psi alpha plus minus is basically the integral over beta of f plus minus beta alpha times phi beta. Just check, delta beta minus alpha put here would give you the phi alpha part, and this thing of course is the second term in the Lippmann-Schwinger equation. So now, what you can see here is the following. If you take the beta gamma at element of f plus minus is dagger, which means of course the gamma beta at element of f plus minus is conjugated, and multiply it by the gamma alpha at element of f plus minus, sum up over all gamma, you should of course get the beta alpha at element of the product matrix. And let's now check what that is. You just multiply the two things out and integrate over gamma, of course. And if you carry out the integration, it rather trivially becomes this. All you need to check here is delta gamma minus beta into delta gamma minus alpha. That integrated over gamma trivially gives you delta beta minus alpha. This delta gamma minus beta times this. After all, delta gamma minus beta is real, so its conjugation is the same. And you multiply it by this and integrate with respect to gamma. It replaces the gamma here everywhere by beta, and this is what you end up with. On the other hand, the conjugation of this times delta gamma minus alpha gives you this term. And the final term, of course, is the product of these two things multiplied. But if you now go back to the identity that we had just derived, namely this one, you can see that these three terms added together is exactly 0, which means that this is delta beta minus alpha. Now, that essentially means that the matrix F beta alpha, or matrix whose elements are F beta alpha, actually is an unitary matrix. And since what this is telling you is that the in and the out states are basically obtained from the free particle states by applying this particular matrix, the unitarity of this guarantees the psi alpha plus minus are going to be orthonormal. If you want to see this worked out in detail, the details are simply here. The inner product of psi beta plus with psi alpha plus or psi beta minus with psi alpha minus is simply these two inner products, the inner product of these two vectors. And now, you just use the fact that f gamma beta plus minus will come out as its conjugate antilinearity in the first factor of the inner product. And from the linearity of the second factor, f gamma prime alpha plus minus, there's a plus minus here, will come out intact. And then using the fact that phi gamma and phi gamma prime are orthonormal to each other, you end up with the delta gamma minus gamma prime from here. Use that to trivially work out the gamma prime integral, and then using the result we had just derived, show that this is delta beta minus alpha. So the orthonormality of the in and the out states have been established. In order to prove the unitarity of the S matrix using this approach, we go back to our original equation about t plus minus alpha beta star minus t beta alpha plus minus, and then multiply both sides of this equation by delta of E beta minus E alpha. Now when you do that, what changes on the right hand side is the following. The E beta here can be replaced by E alpha simply because this expression ensures that the whole thing vanishes on both sides, of course, unless E beta is exactly equal to E alpha. Now with this change, this particular calculation of the fractions simplifies to this. And if you now focus on the part written in red here, epsilon by E alpha minus E gamma whole square plus epsilon square, it is obvious that in the limit epsilon going to 0, the limit that we are interested in, this quantity vanishes unless E alpha is equal to E gamma. But if E alpha is equal to E gamma, this quantity actually diverges in the limit epsilon goes to 0. And it is a very trivial calculation to figure out that if you were to integrate this with respect to dE from minus infinity to plus infinity, the result will always be pi. So this expression in the limit epsilon goes to 0 is exactly the Dirac delta function with E alpha minus E gamma as the argument. It vanishes everywhere unless E alpha equals E gamma. But the area under the curve is exactly equal to pi. So this is pi times delta E alpha minus E gamma. So this is the expression that we end up with. TR plus minus alpha beta's conjugate minus T plus minus beta alpha multiplied by delta E beta minus E alpha is this integral on the right hand side with two delta functions, delta E beta minus E alpha, which was already there, times delta E alpha minus E gamma. Now, in order to proceed further, all we need is our expression for the matrix element S beta alpha in terms of the T plus beta alpha that we had derived earlier. And after that, all we have to do is calculate these matrix elements by simply replacing S gamma beta and S gamma alpha by corresponding expressions from this. Of course, taking the corresponding conjugate for the S gamma beta star. And after this is a very straightforward trivial calculation which I am not going to bore you with the details of. You just multiply this out and integrate using delta functions and you are going to end up with this result. And from the identity that we have just proven, these pieces add up to 0. If you take the twice I pi delta E beta minus E alpha common out of all three of these factors, you can actually take the delta E beta minus E alpha out from this factor because that's exactly what this becomes because of the E gamma integration within gamma. Then these three terms add up to 0 and you are left with delta beta minus alpha, which is what you need to prove that S dagger S is the identity. Very similarly, you can prove SS dagger is identity using exactly the same method. So we have ended up proving that the S matrix is unitary. So we have met a very important player in the theory of scattering today, and we have seen several of its important properties. What is going to be very, very important for us is to take a look at the symmetries that the S matrix has and what consequences do those symmetries, especially Poincare symmetries, have for physics. And this is what we are going to investigate starting from the next lecture. Bye for today.